There are various vocab terms we're going to be learning and how they relate to potential energy. So first we're going to go over vocab. Here we have two terms that are very different. They sound similar, and that's because of prefixes in science. We use the same prefixes to mean the same thing, and it's just an easy way of knowing vocab terms in science as you go into other, STEM courses. And so that's why they sound similar, but they are very, very different. So you want to be very careful. So we have intramolecular force versus intermolecular force. And so you can see in the diagram the differences between the two. So intra is going to talk about within something. So in this example, we're within the covalent molecule, and so we're going to be talking about this bond here. Intermolecular force is going to be unit 3. We're going to talk about the interactions between, for example, here, one molecule to another one based off these partial charges. That is one example. Again, we'll talk about it more in unit 3. So for now, we're going to focus on intramolecular forces versus inter. Make sure you know the difference. It is very easy to confuse the two. Within bonds, we have two different terms. So we have the bond energy, which is, as implied, the energy inside of a bond, and it's stored within that. And so this bond energy is an interaction, and it's based on a number, and that number will show how strong that interaction is within a bond. The other term we have is bond length. And bond length is pretty self-explanatory. It is the distance between the two atoms, regardless of what bond we're talking about. And so this distance is pretty much where the system has a certain amount of energy, and we're trying to keep it at a minimum. And if that doesn't make sense, I will show graphically how that makes sense. And this system could be different kinds. This system could be ionic, and then we talk about the bond length of an ionic bond, or it could be covalent, where we talk about the shared electrons in the middle and that bond. And so we're going to be talking about graphs. In these graphs, we see potential energy, which I'll get into more details in a second. We're going to first define what this potential energy, or PE graph, is. So first we have this line here. It's all dashed up at the 0. And this 0 line is defined as two atoms totally separate from each other. So you can see these two H atoms. There is absolutely no interaction between the two because they're too far apart. Since they're too far apart, there is no attraction. And this graph in general is talking about attractive forces and also talking about repulsion if you get too close. So we're going to go slightly backwards when reading this graph just to get a feel for it. So again, here is where we're too far away and it's not going to interact. As we move down this curve here on this graph, the atoms are getting closer together. So as they get close together, they're going to get more attracted to each other and eventually reach this point, which is the bond length. And so these attractive forces are in that bond. And as a reminder, we have the electrons in the middle, and the electrons in the middle are interacting with the protons of one atom and the protons of the other. And so that's why they're attracting in order to form this bond. You can see on this x-axis here, we have 74 picometers, and that would show the length of that bond as it's labeled here. So make sure that you can read the bond length. It is always going to be the bottom curve down here. Also, as a reminder from the previous unit, there are attractive and repulsive, forces involved. So make sure that you know that this is the point where it's nice and balanced, where they will actually form a bond. Now notice, the energy is negative. And negative energy, well, that doesn't actually exist. There's no such thing as negative energy. We use negative when it comes to describing the direction energy is flowing. So when we have negative energy, we are actually releasing energy. It's going to be an exothermic process. So when a bond forms, it is exothermic, aka energy is released, aka we define it at a negative energy. Some graphs will have a scale here, so if it shows you a number or, a scale, you should be able to get the number of whatever the potential energy units are for this graph to determine where it would have its bond here. And with bonds breaking, it would be the opposite. So like I said here, this bond formed. And so since this bond formed, it's going to be an exothermic thing, an exothermic process. Versus if I break a bond, that's going to be endothermic. I need to input energy in order to break that bond. As I continue reading this graph, so I'm going to go backwards again, I continue going up, I have the atoms getting closer and closer together, and then eventually I am way too close. And when I'm way too close, the forces between these two atoms are very repulsive. As a reminder, we have protons from one H, protons from another H, and so they're going to really, really be repulsive, and that's why you need a lot of energy in order to put this together. Ideally, they do not want to do this. So a couple reminders from general chemistry, and we'll interlock that with AP Chem stuff too. So we have different kinds of bonds. And so single bonds have a pair of electrons in the middle, versus double bond has 2 pairs, which is 4 electrons total, and a triple bond has 3 pairs, which is 6 electrons in total. And so make sure you remember that. Again, that's from Gen Chem. And the things we need to know is how long they are and how strong they are. And so we can notice as the bond length increases, so if I go this way, then the strength decreases. So the farther atoms are together, the weaker the attraction is. So you can see that also with any of these diagrams, really. And so you want to make sure that you know that. Again, as bond length increases, bond strength decreases. So that means triple bonds are going to be the strongest kind of bond in comparison between the other bonds, but they're also the shortest. You can see that with this example over here. So these are all hydrocarbons, and you can see the triple bond here is smaller compared to the double and the single. And so again, because they're really close together, it's going to be the strongest kind of bond between these. Now, if there were different kinds of atoms, you would need to take other things into consideration, but this is a good general trend to know. Now, why is this the case, right? If we have more electron pairs attracted in an atom, well, they're going to hold the atoms more together. They're going to pull them a lot closer. We also need to know this term bond order. The bond order is literally the number of bonds. And this can get complicated real quick because at first it sounds very intuitive, right? Oh, we got first order, second order, third order. But it gets way weirder when we have to think about a whole molecule. You'll see what I mean later. So going back to the PE graphs with bond order, we're talking about simple bond order for now, you can see that higher bond order is the highest bond energy, which is the largest potential energy. So we can see that literally in these graphs. So again, these are the same graphs as earlier, just with less information on it. So you could see this triple bond, the potential energy is huge. You could see that there is a lot of distance between the 0 mark and wherever it designates, versus a double bond is slightly higher and a single is even higher. So you could see the differences between those there. So again, the reason why is there's more electrons pair that are attracting the atoms, they're holding the atoms together, and therefore they're pulling those atoms closer together. So again, triple bond is strongest, so it has the most PE released, and it is the shortest, so just know that. You can also see the distance between where the curves are slightly. If I overlapped them, it probably would have been better. But you can see the difference between single and triple. You can significantly see triple being a lot more to the left compared to the single bond here. And so remember, this is talking about distance. So it's literally showing that the triple bond is smaller compared to a single bond, which is whatever the measurement here for the distance is. So this is showing, again, bond order with PE. And here's the original graph we had earlier, just for comparison's sake. So let's talk about PE when it comes to atoms in the same column, or the same family in this case. And let's compare chlorine and iodine, okay? So let's imagine stuff we learned from the previous unit. So chlorine has a certain amount of energy levels. Iodine has a certain amount of energy levels. And because iodine is so much lower on the periodic table, it's going to have a higher atomic radius compared to chlorine. And so let's think about that in terms of this graph. So I have the H2 graph from earlier, but let's pretend these were chlorine, for example, and then they had whatever chlorine's data is. So because chlorine has a smaller bond length, remember we're thinking about the atoms and their bonding together, the two chlorines, because the bond length is smaller, that means we need more energy to break the bonds versus iodine. Iodine has bigger atomic radius, and so therefore the bond length between two ions are going to be greater. And so because that bond length is greater, we're going to need less energy to form that bond. So imagine the graph, right? If we have chlorine versus iodine. Chlorine, again, is going to be closer. So that means the bond length should be more towards the left compared to iodine. Iodine is going to be more towards the right because, again, it's going to be bigger. Then we think about the curve part of the graph. So if this was chlorines, for example, then iodine is going to need less energy to form its bond because it's farther away. Make sure you can draw a rough graph of this. So you should be able to draw a rough chlorine graph, and then on top of it you should be able to draw a rough iodine graph in comparison. That's a pretty common FRQ for AP Chem, so make sure you could do that. You can also draw a generic one. Sometimes they'll ask you, hey, draw a potential energy graph for some kind of atoms. And so like you would draw the curve, make sure you have a curve go down, make sure it approaches 0, and then you have a too close area. Sometimes the AP test will ask you, oh, what is this part of the graph mean? And so you should be able to interpret that kind of stuff. Here are 2 questions for you to answer. So we have the first one here is a multiple choice question that is related to this section. And then number 2 is an FRQ. So read this hint if you need the hint for this. And then again, these answers over here correspond to number 1. So pause the video and try it yourself before I explain. Ready? Here we go. So for 1, it's just D. It literally follows the graph that we just looked at. Everything else doesn't. E is very close, but notice that there was a curve on top before it leveled out. So make sure that it levels out before the 0, right? And then none of the other ones even match. Not even close. So make sure, again, know the shape, and then know the parts of it, know where length is, how much potential energy, where is it far apart, where is it too close, where is the bond actually forming, that kind of stuff. Now let's go to the nitty-gritty one. I decided to have the different Lewis diagrams for all of the molecules that were here. So I have hydrogen, oxygen, nitrogen. That helps a lot with the hint. So knowing single, double, triple bonds as explained earlier. So the one in the middle, this one right here, that one is going to be N2. Let's think of some reasons why. Well, first, N2 has the highest bond order. It's a triple bond. And when you have a triple bond, you have the smallest length, which has the highest energy. And so when you have the highest energy in that bond, you have the largest potential energy formed. And so looking at these various curves, it has to be N2. That makes the most sense. So now we look at the other 2 choices for X and Z. And so let's figure out where O2 is. So O2 is a double bond. And so a double bond will have the next highest PE after the triple bond. And so looking at these 2 graphs, we can see that Z2 is lower. Ever so slightly, you can see here versus here. And so since Z2 has a potential energy that is lower than X2, that has to be oxygen because, again, it has the most potential energy, the next most. H2 has the lowest bond energy, and so that potential energy is here, which is why it's slightly higher. Remember, the negative numbers are purely to show direction of the energy, so these are all exothermic, and so that's why H2 is going to be right there. Cool? And so bond order for this case is more important than atomic radii. So we could have thought about the atomic radii based off the periodic trend. We could look at that, but that doesn't really trump the fact that, again, these bonds are so much stronger when they're triple versus double versus single. So if I had to write this as an FRQ answer, I would say X2 equals H2, Y2 equals N2, and Z2 equals O2. Or you could say X2 is H2 and so on. However you want to say it. You can also say the elemental, actual names. That is totally fine. In section 2.3, we're going to talk about ionic intermolecular forces, aka we're going to talk about ionic bonding, the attractions between those, electrostatic forces, that kind of thing, because I feel like it is its own thing. So we focused mainly on covalent compounds in this particular section, and then we'll talk about ionic in the next ones. So that's pretty much it for this section. It's not too bad. It's again just looking at the covalent bonds, how it relates to each other in a potential energy graph, seeing what the graph even looks like, and then being able to draw the graph, being able to interpret the graph, and being able to potentially draw another curve on that graph when comparing two or more different kinds of molecules together. All right, that's it for this section. Bye.